So driving home this concept of using the syllabus, in particular the stuff that they ask you that you should be able to specifically describe the formation of these covalent bonds as well as use dot and cross to represent each of these. I'll just very quickly start from the display formula, and by drawing the display formula we can associate hydrogen forming single covalent bond, hydrogen only forms single covalent bond. This is a single covalent bond, so what we could do is we can then convert that into dot and cross. One single covalent bond represents two electrons being shared, and there are no other lone pairs on hydrogen because there's only one outer shell electrons on each hydrogen, and you use it for bonding, and that's nice and happy because hydrogen electrons are in the first shell. The first shell, electron shell, can only accommodate 2 electrons maximum, so that is nice and happy there. Okay, chlorine on the other hand, chlorine is in group 7. So chlorine is in group 7. You can of course also think about fluorine, bromine, as well as iodine because they are in the same group. So if I draw chlorine, I have drawn a single covalent bond because between the two nonmetal atoms, when you get covalent bond, the 7 outer shell electrons of chlorine just need 1 more electrons to go to 8 electron, which is the closest to itself for forming for getting to a noble gas electronic configuration. That's why the halogen typically forms single covalent bond, but it does not mean that they cannot form more than 7 outer shell electrons because chlorine is a third period element, so it can actually have more than 8 electrons in the outer shell. But most of the time, chlorine molecule on its own is definitely a single covalent bond. So I'll draw a single covalent bond as represented by dot and cross, and I'll be extremely wrong because my display formula does not show me the lone pair, but my dot and cross must take into account that chlorine is in group 7, therefore it's got 7 valence electron. It only uses 1 of 7 for forming covalent bond, so I still have 6 more valence electrons on the chlorine. So chlorine has 1, 2, 3, 4, 5, 6, 7. It shares 1 with the other chlorine atom, so it's got 8 electrons in the outer shell of this chlorine. Same deal with the other chlorine atom, except that I draw with the dot. It's nice and easy when you start from display formula correctly, and you can just draw the dot and cross correctly, and that is the way that I would advise you to move forward in this manner. Yeah. The next thing, I'll just jump straight to HCl, which is actually one of the things they mentioned here. Because they mentioned HCl in the syllabus, the associated molecule would have been HF, HBr, and HI. So these are all what you call hydrogen halide, as I said earlier. So the halide would be chloride, fluoride, bromide, and iodide, and all of this is a single covalent bond between hydrogen and the halogen atom. So specifically for HCl, I will draw dot cross Cl, but do not forget, just like the previous example, chlorine is in group 7. It's got 6 outer shell electrons remaining after it uses 1 out of the 7 for forming covalent bond. So that is done, that is done, and that is done. Now I would like to move on to H2O. So oxygen form 2 covalent bond maximum. Hydrogen form single covalent bonds due to 1 electron in the outer shell. So oxygen is in group 6. Therefore 6 valence electron. 6 plus 2 giving you 8 valence electron. So oxygen form 2 covalent bond. Oxygen uses 2 out of 6 for bonding. You are still left with 4 more. You can count properly: 1, 2, 3, 4, 5, 6 for the cross, and dot on the hydrogen. This is not dot and cross. So to show dot and cross hydrogen, dot cross hydrogen, cross oxygen, cross oxygen. If you like, you can use cross for hydrogen and dot for oxygen. As long as your electron count is good, then that will happen all right. Then there's Ch4 and Nh3. Perhaps I go to Nh3 first. NH3, nitrogen is in group 15, 5 plus 3, therefore 8 electron in the outer shell. Nitrogen group 5. Group 15 is what the A-level students would use. But anyway, So we use the Roman numerals. So 5 plus 3 give you 8. Therefore, you form nitrogen form 3 covalent bonds. I would say usually, because we'll talk about another scenario in another topic in another time. Okay, so there is not dot and cross, this is dot and cross. Each covalent, single covalent bond will represent with 2 electrons in the bond as the bonding electrons, because these are the electrons that form single covalent bond. Okay, so don't forget there is a lone pair on the nitrogen. There is 2 electrons that are not used for bonding, because 1, 2, 3, 4, 5. It's easier to start from the display formula and get the dot and cross. The other one is of course CH4, as I mentioned. Carbon is a very important atom because all of organic chemistry relies on this. Group 4 for outer shell electrons, hydrogen forms single covalent bonds. So altogether we get these 4 single covalent bonds, and you can imagine that the carbon having 4 valence electrons. It shares 4 other electrons from 4 times hydrogen, and therefore the carbon will have 8 valence electron, and that is a completely filled second shell, because second shell is the valence shell for carbon. Of course you still have the 2 inner shell electrons, but when we form covalent bond or when we form ionic bond or any sort of bonding, is to do with valence electron. Chemistry is to do with reacting the valence electrons rather than reacting the inner electrons, or rather than reacting the nucleus. We actually only react the outer shell electrons. That is the basis of chemical reactivity. Okay, so what's the other example? We're left with oxygen molecules, CO2 and N2. So I'll do those simple molecules first. CO2, carbon form 4 covalent bond, 1, 2, 3, 4. Oxygen form 2 covalent bond, can be 2 single bonds like this, or can be a double bond like this. And this is very similar to this concept of diatomic oxygen. So there is a oxygen double bond, so there's oxygen cross oxygen. Oops, that is actually wrong. So you have to have dot cross for the oxygen. And don't forget oxygen is in group 6, so it's got 6 outer shell electrons. It uses 2 out of the 6 electrons, so you're left with 4 non-bonding electrons. So electrons that are not used for bonding, there are 4 left after you use 2 out of the 6 valence electrons for forming 2 covalent bonds. As you see there, 2 covalent bonds, a double bond. So this is kind of similar, but the carbon there form 4 covalent bond, just like carbon here form 4 covalent bond, except that here you have a double bond and a double bond. So you convert that into dot and cross. So if I use cross for carbon, there will be dot for oxygen, and the carbon has 4 outer shell electrons, 1, 2, 3, 4. So there are no more non-bonding electrons. So non-bonding electrons mean the electrons that are not used for bonding, essentially the valence electron, they are not used for bonding. It's all completely used up for carbon, but for oxygen, each oxygen will have 4 more unpaired electrons. 4 more non-bonding electrons. I need to be careful of the word I use. I keep on saying unpaired electrons because that is essentially the term that you will use when you go to A levels. Okay, so in O level you can just be thinking about bonding electrons, non-bonding electrons, non-bonding electrons, bonding electrons. Alright, so the next bit is nitrogen, triple bond, because group 5 outer shell electrons, 1, 2, 3, 4, 5. It forms 3 covalent bonds and share 3 other electrons from the neighboring nitrogen. So there is, if I want to show the difference between the 2 nitrogen electrons, I'll use dot and cross to represent the difference. Cross, dot, nitrogen. Don't forget the lone pair on the nitrogen, because you know how to count number of electrons. All right. There were just 2 more examples there from the syllabus that I just want to show you how to get the dot and cross by drawing from the display formula, and by checking the display formula where you show every single covalent bonds correctly. CH3, hydrogen and carbon form single covalent bond. You have O, and carbon form single covalent bond to oxygen because your carbon form 4 covalent bond. You already used 3 for forming 3 covalent bond. You're left with just 1 more electrons on the carbon, and therefore 1, 2, 3, 4 carbon form 4 covalent bonds maximum. Okay, so it's a single bond to oxygen, but remember that oxygen forms 2 covalent bonds per oxygen atom. So it's a single bond to the hydrogen here, because 2 single bond is the same as 1 double bond. Well, when I say it's the same, what I mean is oxygen form 2 covalent bond maximum. It can be 2 single or it can be 1 double. All right. C2H4. So in C2H4, if you start by drawing CH2, so C2H4 can also be written as CH2CH2. If I start by drawing CH2 and I have another CH2, then I will have a single bond between carbon-carbon. Then something is wrong, because the hydrogen to the carbon is single bond, which is nice and happy, but the carbon there only has 1, 2, and 3 covalent bond, and carbon still has 1 more electron. This carbon still have 1 more electron, outer shell electron, and therefore they can form another covalent bond. They can share the 1 electron on each carbon, and they form the 4th and the other covalent bond. Now this carbon, looking at this carbon, it has 1, 2, 3, 4 covalent bond. Looking at this carbon, it has 1, 2, 3, 4 covalent bond. So the job now is draw dot and cross. So dot cross hydrogen, dot cross hydrogen, dot cross hydrogen, single bond. If I use cross for carbon and I use a triangle for oxygen, then I'll have a triangle circle for hydrogen. And don't forget that the oxygen there uses 2 out of 6 valence electron, because oxygen is in group 6. You use 2 for bonding, 1 and 2, the triangle. So I'm left with 4 more. So 4 more of this triangle. Okay, this is dot and cross, showing all the outer shell electrons only. For this one, I'll have cross dot. That doesn't sound right. I want to show the double bond, so cross dot carbon. If I use cross dot for hydrogen, cross dot for hydrogen, cross dot for hydrogen, cross dot for hydrogen, that should have been all right. So there are some textbooks and there will be some teachers who will insist on you drawing each of these in shell. Okay, so the hydrogen draws shell, the hydrogen draw the circle to represent the shell, and then you show the sharing of electrons. That is perfectly reasonable. That is perfectly reasonable, and that is perfectly correct. And what I've drawn here really is the simplified version of that, because I'm a very simple man, and I don't like drawing a lot of circles because it's very messy. And you know how it is, right? When you draw one circle like this, and you're like, oh, it's not perfect. This is not perfect, and then you keep on rubbing and you keep on rubbing and erasing and redoing it. It's such a hassle. And for me, as long as you could draw the display properly, as long as you could translate the display into the dot and cross, and you could translate it very neatly and tidily, that it's very easy for the examiners to see it, you would definitely get the marks. Okay, so the shells are not essential, because the shells are not essentially real. Okay, it's not a real physical shell. It's simply a region of space where the electrons are most likely to be found. So again, these are just whatever is stated in the syllabus. They could ask you other similar molecules. It's all about the skill. Can you draw the display formula and translate it into the dot and cross properly? If you know how to count the number of covalent bond based on, is it carbon center, is it oxygen center, is it hydrogen, nitrogen, is it a chlorine, bromine, iodine, fluorine, that kind of thing. All right. So moving on to the next part of this lecture tutorial, the last bit is really talking about structure and bonding. So we already talked a lot on the bonding, so we need to talk about structure, bonding, and properties. Okay, so all the simple covalent molecules, this is their structure, simple molecular structure. And a question say describe in terms of structure and bonding. You have to identify them as simple covalent molecules, and therefore they have simple molecular structure. So in terms of what are their individual lattice particles, we are talking about breaking the weak intermolecular forces between the molecules, or between the atoms. Okay, between the molecules, these are discrete meaning individual molecule. So you see that this is, for example, an iodine molecule. There are 2 atoms and they're arranged in this lattice. okay, where they are existing as discrete molecules. So iodine solid exists like this, iodine liquid exists like this, iodine gas exists like this. Okay, simple molecules, simple molecular structure. When you change the state from solid to liquid to gas, do not break covalent bond. Do not break covalent bond, because what actually break, okay? So a lot of students will be confused because they think about simple covalent molecule. It has covalent bonding. Yes, that's correct. Covalent bond between the atoms. But because they have a simple molecular structure, all you're doing when you go from the solid to liquid, which is melting, liquid to gas, which is boiling, or solid to gas, which is sublimation, you are just breaking the weak intermolecular forces between the discrete molecules. And that is why, because you're just breaking the weak forces of attraction or weak intermolecular forces between the molecules, it has low melting and boiling point. So simple molecular structure, low melting and boiling point, because little energy, small amount of energy is required to break the weak intermolecular forces between the molecules. So it's a bit redundant because intermolecular already means between the molecules. It's the force attraction between the molecules that you break specifically for simple molecular solid. All right, so be very careful about structure. The other one that's really stated in the syllabus is to do with conduction of electricity in relation to what ionic compound could do. So ionic compounds can conduct when they are liquid or aqueous. However, simple molecular solid, simple molecular compounds, they do not conduct electricity, when solid, liquid, or aqueous, okay? However, I mean, this is the reason for it, no free electrons or no free ions. However, you need to be careful of this, all right? So this is HCl gas. It's at room temperature, it's a gas, it's a HCl covalent bond. This is called hydrogen chloride. When I dissolve this in water, in liquid, it can give you HCl aqueous. HCl aqueous is what you call hydrochloric acid, and HCl aqueous is a mixture because it contains water as well as HCl dissolving in water, and you get HCl aqueous, which further dissociate into H plus and Cl minus. Later on in O-level or IGCSE chemistry, you will learn that this is called the acidic proton. You know it as a proton because hydrogen has a single proton in the nucleus of the atom. When you have a H plus, you have lost the only electron in the first shell that you have. Therefore, there is no other subatomic particle apart from a proton. This is called an acidic proton, except when you have the heavy isotope, which is hydrogen 2. This is going to be assumed to be hydrogen 1, which is the most abundant isotope of hydrogen, because the relative atomic mass, which is the average mass of all the isotopes of that element, relative to the mass of an atom of carbon-12 times by 1/12. That is the definition given in the atomic structure topic as required by the syllabus. It's new in the syllabus. Definition of relative atomic mass is required in the syllabus, and because the average mass of hydrogen as given in the periodic table is 1, this tells you that hydrogen 1 is the most common isotope. Well, enough recap, I guess. So I just really want to drive home the message that simple molecular solids have simple molecular structure, therefore low melting and boiling point. You've got to explain it in terms of the force of attraction that you need to break, and they also do not conduct electricity, partly because there are no free electrons. I don't really like the idea of free ions, because that's really saying that they are ions, but there are no free electrons to carry the current. So most of them do not conduct electricity when solid, liquid, or aqueous. However, in some cases where you get this compound here, can dissociate or can ionize to form these ions in solution. So these ions, these free ions in solution, can conduct electricity. So if you have hydrochloric acid, they can definitely conduct electricity, but hydrogen chloride do not conduct electricity, okay, because it is not the acid. There is no water in it, okay. Do not conduct electricity in solid, liquid, or gas, okay, because they exist as single discrete simple molecule, exists as single individual discrete molecules. They are not ions being formed, but in water they do form these ions, only for acidic substances. So that's the end of this lecture tutorials, the second part of covalent bonding, and we cover structure in the first bit. I taught a little bit on the dot and cross, which we can get by getting the correct display formula and counting the number of covalent bond correctly based on the group number of the central atom, telling you how many valence electron does it have, and therefore how many electrons do you need to get up to noble gas configuration. Okay, we also discuss on properties of simple molecular, simple covalent molecules which have simple molecular structure. So if you got any questions, feel free to comment on the video, or just ask me if you see me in school or whatever. Okay, so yeah, that's it. Thank you for watching, and don't forget to subscribe to the channel, as well as follow me at ptet.chemistry, ptet.chemistry on Facebook, IG, or Twitter if you use this social media platform. Alright, so see you in the next video. Thank you for watching again.